Okay, well, what if we have a logarithmic function? Well, we're going to do the exact opposite. Okay, a logarithmic function is an equation that contains a variable in the logarithm. Okay, so first thing we want to do here is we want to get that logarithm all by itself. So we want to get that 3 out of there. That's the first step. And then we'll have log base 4 of x plus 5 equals 6 minus 3 is 3. Now we're going to rewrite this in exponential form. So the x is inside the logarithm. So what we want to do is change it into exponential. And now we have 4 to the third equals x plus 5. And that should be looking fairly reasonable to solve there. So we got 4 to the third. 4 times 4 is 16 times 4 is 64. X plus 5 equals 64. Subtract 5. X equals 59. Okay, now we do have to check this here because the domain of a logarithm, if we have a logarithm, the stuff inside must be greater than 0. You cannot take the log of 0. You cannot take the log of a negative number. So we have to check. Here we got an answer of 59. So the question is does 59, does it work for this problem? So if we plug 59 in, let's try it out here. So we have 3 plus log base 4 of 59. 59 goes in here, it becomes 64, right? So 64 equals 6, and let's just think about it here. So 4 to the third power equals 64. So this is 3 plus the 3 that we had equals 6. All right. That's the ticket there. Okay, 59. Okay. All right. So let's try a couple of these just to kind of wrap this up here. Whoa. Lock that down. All right. So just the reverse of exponentials. We want to get the logarithm all by itself, and then we're going to change it into an exponential. Okay, so get that 3 out of there. So log base 8 of x plus 5 equals negative 1. Now it's time to change it. So 8 to the negative 1 equals x plus 5. All right. So if we subtract 5 there, we get x equals 8 to the negative 1 is 1/8. So we have 1/8 minus 5, which 5 is 48ths. Okay, so this is negative 39/8 when you subtract those. So we get the log by itself, then change it to an exponential. So get that log by itself, get the 5 out of there, that's just being multiplied, so divide it by 5. So we got 9, natural log of 3x. Okay, don't try to pull that 3x out of the middle there. You can't touch that 3x there yet. We got to get the log out of there. How do we get the log out of there? We got to, don't divide by it. We have to change it. Remember, there's an invisible base e there. So this is e to the 9th equals 3x. Okay, so we'll just divide by 3 and we're done. So e to the 9th divided by 3 is fine. Okay. Okay, how about this one here? There's an invisible 10 down there, so let's swing it around. So this is 10 to the first, and that has to equal 3x squared minus 2. It's down to a quadratic. Let's add 2 to both sides. 3x squared equals 12. Divide by 3. And we've got an x squared equals 4. And that leaves us with a plus and minus 2. Don't forget your plus and minus. We get plus or minus 2. Okay, now remember we've got to check because we have a domain restriction, kind of like with square roots. Remember, square roots had some numbers that didn't work. They looked like they did, but in the end they didn't. So let's check. Log of 3 times 2 squared minus 2. So that is 3 times 2 squared. That's 3 times 4. That's 12 minus 2. So that's 10 on the inside. And that does equal 1. Check. Now, if we plug negative 2 in there, well, it's going to square and still become positive. So it works also. Okay, negative 2 is going to give us the same. So we do have 2 answers there. Okay. We didn't check this one, but we should. So if we have 5 times the natural log of 3 times e to the 4th, no, e to the 9th, right? Can't read my own writing. Okay, so here the 3's cancel, and we have 5 times the natural log of e to the 9th, and e to the 9th, natural log of e to the 9th is just going to be 9. So 5 times 9, which is 45. Check. Okay, that's the idea. All right. Well, one application here that's useful to see, okay? We have, a lot of times we're talking about populations. We have what's called an exponential growth function. This is our exponential growth function. A new population is equal to the old population times e to the kt. This looks a bit like our compound interest formula, and which we'll look at here in a moment, okay? So P sub 0 is our initial population, K is the growth rate, and T is the time. All right, so the population in Oregon in 2010 was 3.83 billion, okay? And in 2018, the population was 419 million, okay? So let's find the exponential growth rates, okay, over the 8 years there, all right? So we had 8 years. So let's plug that all in. What we don't know is K, all right? So let's get everything in there except for K. So the new value, P of T there, was 419 million, okay? And so that is equal to the initial population, 3.83 times e to the kt. K we don't know, t is 8. All right, so let's divide by 3.83. And using a calculator, we get 109 there, 109.399. 399, and that equals e to the k8, k times 8. Now let's change this into, it's an exponential form right now, so we need to change it into logarithm form. So swing that base around, and we get the natural log of 109.399 equals k8 times 8. And we'll divide it by 8 to finish that off. And we'll go punch that into our calculator. So the log of that number, the natural log that is, of 109.399, make sure you divide by the close those parentheses, okay? And we got 0.586, it looks like 0.587. Okay, so K is about 0.587. Okay, after you divide this stuff here. All right, so that's exponential growth, okay? And then the last one here where we can use logarithms is, in this case, what if we know we have our compound interest formula that we've seen, and we want to take $200,000 and make it grow into $100,000 at 9% interest rate, okay? So the question is, how long? What will that t value b. So let's plug in the numbers. We want a, which is the new value, 100,000, equals the initial value, 20,000, okay, times 1 plus the rate, which is 0.09, divided by n, and this thing is compound monthly, okay, so that's 12 to the 12t. So we want to figure out how long it's going to take there to go from 20,000 to 100,000, so 5 times bigger. Okay, so let's divide this by 20,000 first, and that's going to give us 5, right? 5 equals 1 plus 0.09 over 12 to the 12t. Okay, now we need to, well, let's go ahead and get that as a decimal. 1 plus 0.09 divided by 12. And that's just 1.0075. So let's change this. It's an exponential function now. We need to change it to a logarithmic function. And so that's going to be our base. So we're going to have log base 1.0075. That feels a little weird, but that works. Of 5 equals 12t. Okay, now we're going to need to divide by 12. So divide by 12. So to do this, we're going to change this into log, or let's go natural log of 5 divided by the natural log of 1.0075. There's our change of base formula. And I got that 12 on the bottom, so maybe I'll just go times 1/12. That's the same as having 12 on the bottom there. And using the calculator, we get an answer of 17.949 or 95. Okay. And that is our time in years. So basically 18 years. Okay. All right. Now that 9% interest is a pretty good rate there. That's what's going on there. So we'll leave it at that. The key again is to, if it's an exponential equation, change it to a logarithm. If it's a logarithmic equation, you're going to change it to an exponential. Good luck.